So it's a pleasure to introduce Adel Javanmard from USC, and it's going to talk about a flexible framework for hypothesis testing in high dimensions.
Okay. Hi everyone. Thanks for coming, and thanks to the organizer for a wonderful workshop. So today I'm going to talk about a general framework for hypothesis testing in high dimension, and this is based on joint work with my colleague Jason Lee at USC. So let me start. Suppose that you are getting n data points. So those are y1, x1 to yn, xn. yi is just the response variable on sample I, and xi is the covariate vector or the feature vector of that sample. And one of the main tasks in statistical learning is to try to fit a model to this data. And confining ourselves to the parametric model, this means that you assume that yi is generated according to this probabilistic model that is parameterized by theta 0. Let's say theta 0 is in p dimension, and you want to estimate this theta 0. And the jth coordinate somehow quantifies the contribution of feature or covariate j on the response variable. So in this talk, I will focus on the high dimensional setting. So the number of samples n is much smaller than the number of dimensions p, and we assume that theta 0 is mostly sparse, so it has only s non-zero coordinates. Now, to make our life easier, let's focus on the linear model. So in this case, y is given by x theta 0 plus some random noise. And I'm assuming w to be normal, but you can relax this assumption. And one of the prominent approach to estimate theta 0 in this case is the Lasso estimator that I think everyone knows. It tries to optimize this cost function that somehow promotes the sparse solution through this L1 penalization. Now, there's a great literature on Lasso in the past 2 or 3 decades, especially in terms of the point estimation. You have different types of guarantee under different assumptions in terms of parameter estimation, variable selection, prediction, and also there are various fast implementation of the Lasso, and it has been widely used in different domains of application, thanks to these great researchers and many others that are still contributing. So in this talk, I want to go behind the point estimation, and I want to talk about the statistical inference on the model parameters. So to be specific, I would like to develop a general framework for doing this sort of hypothesis testing. So the null hypothesis is that your parameter theta 0 belongs to some set omega, and the alternative is just the opposite of that one. And this omega is some pre-given set to you. Now you can think of encoding different types of structure in the set omega, and then if you have this framework, you can test whether your theta 0 has that type of structure or not. And we are not making any restricting assumption on omega, so it could be non-convex or even disconnected. And before I proceed, I wanted to mention that there is a paper by Yin Chu and Yelena that studies the same problem, but the methodology and also type of results are different. But I wanted to highlight this one. So let me continue by some specific example of this set omega. So the first example is when you want to test one specific parameter in your model. So you want to test whether theta 0 I is 0 versus the alternative. And I think Lester gave a very good example yesterday that you had some pricing model and you want to see what's the elasticity, you want to see what's the effect of price on the demand. So that corresponds to, for instance, doing inference on one coordinate. And in this case, you can take omega to be all the vectors in Rp that vanishes on the ith coordinate. And this has been along the problems that have been studied in the past couple of years. And using the duality of confidence interval and hypothesis testing, also if you use your framework, you can get valid confidence interval for theta I. The second example is if you want to do inference on the quadratic form. So let's say Q is some given metrics to you, and you want to test whether the norm of Q theta 0 is in some interval. Okay. This problem is itself very interesting because, okay, if you take Q equal identity, you can do inference on the size of the signal. And in this paper by Lucas, Rina, and Emmanuel, it's argued that if you can do inference on the size of the theta, you can also do inference of on the error of your estimator. So the idea here is to do data splitting. So you split your data into two chunks, y1, x1, and y2, x2. You try to estimate your, let's say, Lasso estimator using the first chunk, so you get some theta at 1. Now, if you define y tilde to be y1 minus x1 theta at 1, this also corresponds to a plugin for y1, so it's x theta 0 minus theta at 1 plus noise. Now, this is your new signal. So if you have some framework to do inference on the size of the signal, this also lets you to do inference on the error.
What do you mean by duality?
By duality, so if you have a framework to do hypothesis testing, this automatically gives you a framework to make confidence interval. So that would be the interval of all the values that you fail to reject.
And duality comes from?
It's just some relationship between these two, so this is sort of granted. The second example is, let's say you have random design. So they are coming from some distribution with population sigma. Now, if you take Q to be sigma half, then you can use this framework to do inference on the proportion of explained variation. So that's the ratio of the strength or variation explained by the signal to the variation in your response. So you can show that this quantity in the denominator concentrates very well. It's a chi-square with n degree of freedom. So if you can do inference on this one, you can also do inference on the explained variation. And this is useful, for instance, in GWAS, genome-wide association study, because it tells you what fraction of variation in the trait can be explained by genes rather than the environment. The third example is, okay, there are many results for support recovery of Lasso, but mostly they require a condition called theta mean condition. So you want the minimum non-zero theta to be above some threshold. Okay, if you have Gaussian design and under some assumption, then you can remove S here. Now, although this assumption is commonplace in the theory, it's hard to verify that in practice because you don't know what theta 0. Okay? Now, in this case, again, you can take omega to be this family of vectors, and you can test whether theta 0 belongs to this set or not. The fourth example is if you want to test over the convex cone. So this is a problem that naturally arises in studying the treatment effect. So these are two important examples. One is the non-negative cone. So let's say theta I is the effect of treatment I, and you want to see whether all the treatment that you have in your study are harmless. So you want to test whether theta is in non-negative cone. Or let's say different treatment corresponds to different dosage of a drug, and it's plausible to assume that if the drug is of any effect, then its effect should be monotone in the dosage that you are using. So you can test whether theta is in monotone cone. And there is a long history of work on these problems in Gaussian sequence model from 63 to present. Okay, and the last example is you can use this framework to test arbitrary functionals of theta. So you can take any function f from Rp to R, and this would be your omega, and then you can also compute confidence interval for f of theta 0. So in particular interest is when you take f of theta to be a linear function, so you can compute the confidence interval for the predictions. Okay. I hope that you are convinced that it's an interesting problem and useful. So this is the outline for the remaining. Yes?
Can the set be random?
The set omega?
Yeah.
No. So it's not adaptive.
Well, if you do sample split, then you can do omega random with your framework.
Yeah, I think by random it means that the omega depends on y and x, right?
Yeah, but if you like, you can design
okay.
on the first
okay,
split.
That triggering always works. Yeah, if you omega from the
trivially
first.
you can do it. I mean, what
Okay, so let me start with the methodology. It has different steps, so I'll go through them one by one. The first one is try to look at the problem. Instead of working with the original problem, I want to work with a projected version of the problem. So this is the null hypothesis that I have. instead of trying to test this hypothesis, I project on some subspace U. So this is what I do. Now it's easy to see that if this null hypothesis is true, then the H tilde is also true. If something is in omega, then the projection is also in omega. So if I can control the type 1 error, the false positive rate for this one, it also controls the false positive for the first problem. But you might lose power if you don't use U wisely enough, because it might be the case that theta 0 is not in the omega, but when you project, it's inside the omega. So you might lose power here. But let's say you assume some good U for the moment. So now you have a problem in k dimension if U is just the basis of that space in k dimensional space. The second step is, okay, so this is the control. That one. The second step is doing debiasing, but in a rotated basis. So let me give you some background on debiasing. So the Lasso estimator is very good in terms of the point estimation. It gives you good estimation error and also the prediction error. But something that's not so good is that it's biased because of this L1 penalty. And in particular, it's hard to characterize the distribution of Lasso in high dimension for general design X. Now, the idea of debiasing was to start from the Lasso estimator and try to remove the bias as much as you can. And then this gives you another estimator called the debias estimator that has less bias, but also it goes under some distributional characterization. So I'm doing debiasing on a rotated space. So if you look at theta 0 in the projected space, these are the coordinates of the vector. So this is gamma 0. And I want to do debiasing directly on gamma 0. Okay? So this is the form of a debias estimator. It has U transpose theta hat, and then you have this extra term. Okay. So I need to define G. So we'll see that in a moment. But this is the general form that you have. Okay. By adding this term, I'm trying to remove the bias of U transpose theta. Now, if you take U to be identity, this becomes the classical debiasing that have been studied in the past couple of years. So what I'm doing here is different from computing the classical debiasing and then projecting, because that doesn't work. Here I'm directly trying to debias U transpose theta. And if you take U to be a vector, then this becomes a proposal that was offered by Tony and Zigi in 2017. So here U is just some metric. How should we choose G? So let's try to play with this debias estimator a little bit. So I plug in for Y. So Y is x theta 0 plus W. And then I rearrange the terms and write in terms of the empirical covariance, sigma. Okay. So you get a bias term here. And this is your Gaussian error, provided that G is independent of W. If G is independent of W, conditioning on X, this becomes a Gaussian random. Okay. So what's a good debias estimator? Ideally, I want to kill the bias, and I want to make the variance as small as possible. Now, this gives you some idea of how you should choose G. So if you look at the ith coordinate of the bias, you can bound it this way. So it's the L infinity L1 nor. And the variance of the debias estimator is given by this function. So both of them depends on G, Gi, the ith column of G. So I want to choose Gi in a way that minimizes both of them. So we do that with this quadratic optimization. So you want to minimize the variance, and you have some constraint on the bias. Okay, so mu here is some tuning parameter. So it somehow play the trade-off between the bias and variance here. Okay, so here you are trying to control the bias, and you are trying to minimize the variance at the same. Now the theorem is that if S log P over root n goes to 0, then this is a debias estimator of U transpose theta 0. So gamma d minus your signal is given by some Gaussian noise. You know exactly what the distribution is, the covariance is. And delta, the bias term vanishes asymptotically in infinity. Now I know that there are some people who doesn't like this assumption. So you can relax this at least for the Gaussian. So you can make S log P over n goes to 0 and get the same thing for the Gaussian design. But for general random design or fixed design, I don't know how to
what's the assumption on x here?
Okay, so I simplified too much. So you can assume either x with sub-Gaussian rows, and the population covariance should have bounded eigenvalues. And if you want to take the fixed design, then you want the coherence number to be positive. And that dictates how you should choose mu here. So mu is chosen depending on the incoherence number of the design.
So this accommodates fixed designs?
Yeah.
So if we go to the result, your slide work. So when I have things going to infinity, what happens to a fixed design when I go to infinity?
What do you mean?
So you have a, let's go to your result, perhaps?
Okay.
Yeah. So there's something, I understand, I interpret this as a well, we use little O notation, so it's an asymptotic result, right?
Yeah.
So what does this mean when I have a fixed design?
So it means that if you condition z on x, okay, this is given by this normal distribution.
Sure, but I need to know what x is, right? When the size of the problem gets large.
Yeah. So, and we get some probabilistic band on delta infinity bigger than, say, mu star. Then some constant.
I think I understand the statement of the result. I think is when I think about problems going large sizes going to infinity, which I think is the result you have. No? How does this fit with a fixed design? What fixed design?
You mean how? Okay.
You need to tell me somehow. There's a deterministic sequence.
Okay, so the way that we do for the fixed design is not in the asymptotic. So you get the probabilistic bound that if you have a design with n and p, what's the probability that this one is bigger than?
That's a slightly different.
Sorry for simplifying too much. Okay, thank you. So that was the second step, that you debias your estimator. And now the third step is, okay, this is the debias estimator, this is your true signal, this is the noise, and this is the bias that vanishes asymptotically. So what I do is that I do an L infinity projection of the debias estimator on the set omega. So this matrix D here is just chosen to make this Z to be normal, standard normal on each coordinate. So it has correlated coordinate, but I want each coordinate to be a standard normal. So this is just some diagonal metrics to normalize things, and then I do some infinity projection. And then the test of statistics is the value of this optimization. And you can see why I'm using the L infinity, because I can control the bias in the L infinity norm. And then this becomes, if the null hypothesis is true, this is asymptotically dominated by the infinity norm of Z. And this is the test of statistics that you use. And then the fourth step is just to do the decision rule. So you take the test of statistics and you compare it with this threshold, and Z alpha is just the quantile of the standard normal. So if I want to summarize, so this is mostly the decision. I need to modify it a little bit because I've not told you yet how to choose U. But if you know what's the good U, then this is the procedure that you follow. You project the problem on subspace U, you debias U transpose theta hat, you do L infinity projection on omega 0. This is your test of statistic, and then you have the decision. So these two are natural. First three steps. Any question?
So what is D again? D is the diagonal?
This one is just the diagonal metrics to make the covariance 1 on the diagonal.
So marginally?
Yeah, marginally standard.
Normal.
Yeah.
That's the difference.
Is the test statistic normal under the null?
No, it's bounded by some normal.
It's bounded by null.
Yeah. So you need to argue that if theta 0 is in the set omega, then the objective is less than when you plug in theta 0 here. Okay, so what's the theory that we have? So let's say you want to get the more important thing than to control the false positive rate. So I define the false positive rate in the following sense. So it's the probability of rejection if the null hypothesis is true. And then I take the supremum over all the theta in set omega that are S squares. Okay? And S is a function of n when you are thinking asymptotically. So this is the theorem for random design. So it has, I think, the assumptions that we need. The design has sub-Gaussian rows and X sigma inverse as sub-Gaussian row, and sigma has bounded eigenvalue. Now in this theorem, I'm assuming U to be any arbitrary fixed U that's unitary. So this is the basis of some subspace, k-dimensional subspace. And it's independent of your samples. Okay? So any U that is independent of this one satisfy the assumptions of the theorem, and you can control the false positive rate. So this holds for almost any U. And you can come up with some analogous results for the deterministics. I'm just skipping that one. Now the question is how to choose U. So that's the more interesting part. So if I want to see what's the good choice of U, I need to analyze the power and then choose the U that maximizes that power. So this is the measure of the alternative strength that I define. If I'm quantified what's the distance of theta from the set omega. You have U transpose here. If there was no U transpose, it was just the distance of theta 0 to the set omega. So you want to see how far your true signal is from the null hypothesis set. And then you can quantify the power of this test. So it's given by some function f. It has 3 arguments. The first one is alpha. This is the level of false positive rate that you have. The last one is k, is the dimension of the space U. It's the space, dimension of the space that you are basically doing your test. And then here, this is the signal to noise ratio, basically. So eta here is the strength of the alternative. And this is the function given for the power. That's good. So the expression might look strange, but let's see how it looks on the plot. So I'm plotting this f of alpha x. So I'm fixing alpha, and then I'm changing x. So there are 2 properties that you should know. The first thing is that if you increase x, so if the signal is getting stronger, then the power goes up. So this is what you expect. And the other one is that it's monotone decreasing in k. So if I increase k, the plot goes down for a fixed x. And so these are 2 properties of this function that I want to use. Now, the choice of this basis U would be basically I want to optimize this power over k. So k could be any number between 1 and p, and U is any basis for the k-dimensional space. So this is just saying that it's a basis, and I want to optimize this one. Okay. Now, can I optimize this? Okay, the first problem is that I don't know what's theta 0. Okay. So if I want to go about this problem, the easy way is to, I use Lasso instead of theta 0. So I replace this by theta hat. But this gives me another problem because I want U to be independent of yi and xi. So if I use the Lasso estimator here, then the U that I obtain depends on theta hat and depends on the data. How do I solve this? I already mentioned that you can do data splitting. So what I do is that I take my data, I split it into 2 halves. I use the first one to get theta at 1, and then I plug in theta at 1 here instead of theta 0 and optimize to get U. And then I use U and the second half to form the Debiasing estimator for, this should be U transpose theta 0. So this is basically what we do. Data splitting. One split is used to optimize and find the U, and then U is used with the second half to to form the D-bias. There might be some way that if you use sharper analysis, then maybe you can avoid the data splitting, but we are not smart enough to do that. Okay, so this becomes a problem that you have. This is theta at 1, and I want to optimize. Okay, so this is an optimization problem, but in principle, you should be able to solve it. But let me mention one case, that if omega is convex, then this becomes super easy. Okay, why it's super easy? When omega is convex, you can argue that the maximum of this cost function is achieved for k equal 1. So there is one, so you need to take k1, and then there is one specific direction that maximizes this power. So what's the idea here? Is that if you look at this, this was the strength of the alternative, the distance of theta hat 1 from the set omega. Okay. So you can write it in terms of min max, and then if omega is convex, you can use the von Neumann's min max theorem and swap this min and max. And then you can show that for any u, there is one vector u such that this holds true. So there is one u such that if you take the vector little u instead of the space u, then the distance would increase. Now use the properties of the function f. So it was monotone increasing in the second argument. So I replace the second argument with this one, showed bigger. And then I use the second property that this is decreasing in k. So I replace k with 1. Okay, and I get this one. So I need to optimize this function. So I can assume k is equal 1, and u is just some vector u. And you can indeed solve this. It has a closed form, and the closed form is given by this one. So what's p of omega? It's just the orthogonal projection on the set omega. And arc mean of theta minus 3 to what v is in omega. Projection omega of theta. And then the orthogonal projection is just theta minus the projection over omega. And then you just normalize it to give that what's the direction of the vector. So it has a closed form for the convex omega. But for the non-convex omega, there is no closed form. You need to do that case by case. So for instance, in the case of testing the theta mean condition, your omega is non-convex, it's even disconnected, but we are able to see what's the solution for that case. But there is no closed form for any non-convex omega. Any questions? Yes?
So when you define type 1 error or the false positive rate, you only consider those sparse thetas in this omega. But then when you talk about power, why don't you just restrict yourself into that set instead of the whole omega?
Okay. This one, remember.
Because in your type 1 error, you have an extra restriction that's the 0.
Yeah, but I think that wouldn't change the argument here because you are replacing theta 0 by theta at 1 and both of them are sparse. I think it doesn't change the argument. But I'm not sure if I need to look up the details. I don't remember if the power is defined over the sparse signal or...
I guess my point is if you only look at the sparse signals, then omega cannot be convex.
Okay, so that would be a relaxation of that one. Thank you. So if we go to the examples, the first example is if you want to do linear functional. So your omega is v transpose theta equals to some given constant c. Then in this case, u is just given the vector v. So it's the new covariate vector that you have. And you can show that this gives you the minimax optimal. So this recovers the proposal by Tony and Zijian for prediction. If you consider the quadratic forms, then this becomes basically theta hat 1. So you need to do debiasing, but in the direction of the lasso.
You mean omega is less than equal, like the norm square is less than or equal to C, perhaps? Like omega convex, doesn't matter?
Yeah, yeah, you can replace it. Okay, so let's go to the numerical experiment. I think I'm good on time. So you have y equal x theta 0 plus noise, and for sigma I'm using this type of sigma ij is just rho to the I minus j, so it's decaying as I and j are becoming far. And then I choose S uniformly at random from 1 to p. The size is S0. Then if you are in the set, this should be S, I guess. It should be B when you are in the support, and it's 0 otherwise. Now this one is when you want to do, when you use this framework to do hypothesis testing on the non-negative cone. So when I take B to be less than, let's see. Okay, so if I take B to be positive, then this becomes type 1 error. And if I take B to be negative, then this becomes the power. Okay? So if I compute the probability of rejection, in this case it's just the type 1 error. In this case it's just the power. So you see that it's conservative here, so it's not 0.05. But the power is good. So if you are already like 0.4, you get power 1, and also here rho is the correlation of the sigma. It also has good control over different range of correlation. The second example is for the beta mean condition. So this is the non-convex set omega. But as I said, you can compute what's the right U. I don't have the formula on the slide. But again, you see here, if you take, so B is 1, that's the true signal. So if you take C to be less than 1, this becomes a type 1 error. If you take C to be bigger than 1, this becomes power. And again, see that the power is good. And it controls the false positive rate. And this is for inference on the predictions. So this is the 95% confidence interval, so it's around 95% that we set. And these are the length of the confidence interval, so it scales with basically the norm of sigma over root n. This is the log plot. It's linear on that one. Okay, any question? Yes, I think with this one I can conclude the talk, and I would be happy to take any question.
What if your samples are dependent? Would the data splitting scheme still work somehow?
Yes. Sorry, could you speak up?
What if the samples are dependent?
If the samples are dependent.
Right.
Even I think the estimation part is hard. I've seen I think 1 or 2 papers that do the point estimation results for Lasso for correlated samples, like in the time series and active learning. But it's something not, I would say, it's not very well understood. Yeah.
Regarding the sample splitting, the first question is if you would not split it. I understand the theory would not go through, but would the simulations be okay? And the second question is, in the simulations this looks fine, but if you do it on a single data set and you split the sample, do you see a lot of variation depending on how you split the sample?
Okay, so
that is in our experience sometimes quite a problem. So you, and of course in practice you have a single data set, you split the sample, and you do the sample splitting 100 times, and then you can compute your p-values, how much variation is there.
So the answer to the first one, if you don't do data splitting on simulation, it works. So I expect that there is some sharper analysis that go about that one. And the second one, yes, if you do splitting, you see the variation on how you split. So I think the best way is either to do some boosting if you want to do the data splitting, but I'm hoping that someone can prove it without data splitting.
Okay, I can. So actually, you can aggregate. I think again,
There is
you do
problem.
randomly, but of course they're dependent, and but at least you can do something robust.
Yeah, so it's something similar to the boosting that you have for the p-values. Yeah, so I think it should work.
But of
I've
course,
not
the
looked carefully.
trouble is, in a way, the theory says it's fine, but if you actually
Right.
and of course we don't see it in simulations because it's averaging.
Yeah.
So it's but in practice, you would recommend not to split the.
Yes, I tried, and even okay. So in real data, I take the riboflavin from your HDIR package, but it's semi-real data because I'm making noise again myself. So in semi-real data experiment, this one, it doesn't matter, but I don't know how to prove it.
All right, let's thank Adel again. So I guess at 2 p.m. there's lightning talks that are